is money. Money is time. Machine, wake up. Yeah. This will go for this is for a learning system. Third lecture. Save. Is okay. A learning system is okay. Recording started. Broadcasting okay. This is not needed. This is not needed. This also no longer needed. This also no longer necessary. No one. No one. Okay, let's go forward. I have prepared something electrical. It's on the table. So I have a regulated DC power supply. I have ammeter, I have voltmeter, I have also wattmeter. All these powers, some network, and network is loaded with this nice ball. Here, I have power. I can bring the camera closer to make my instruments big. So it's visible. Here is the voltage, here is the current, power in watts, and I have one more. Let's say this is one. I have put another secondary side voltmeter. This one shows 12. Okay. Simple schematics. Simple. Now I would like to draw a table. DC source in volts and current in amps. What do we see? A bit more closer. 26 volts. Yeah? And 107 ohms. You see? 26, 107. I can write here. 26, 107. Okay. I can 24. 2403. And current 1 on 15. Good. Let's go down. 2201. 22. Exactly 22. And we have 126. Okay, next point. 20. 2003. What we got? 1, 7. Okay, I can do one more. Something like 18. $17.99 and 154. So we have something, isn't it? At 17 it still works. 1707, 163. Okay, this is enough. What do we see? Decrease voltage, decrease, current increase. And what about Ohm's law? By Ohm's law, increase in voltage should increase current. Decrease in voltage should decrease current. And here we see the opposite.
Yeah.
What's going on? Yeah. But why? It's against the Ohm law. It's against basics of electrodynamics, isn't it?
Yes.
Something wrong here. Oh, you're missing the interesting thing. Okay. Drop your back and take a look on this network. See voltage, 17 volts.
17, okay.
What happens if I increase voltage? And this is current, 1.64. What will happen with if I increase voltage?
The current will be increased.
Watch it.
Why the current is down? Because you're connecting resistor.
It's a load. It's an active load. Look here. 25.8, 1 ohm. 18, 1.46. 17, 162. What will you? Is it what you think about it? It's against Ohm law. Current should be proportional to voltage. Yeah.
Yeah. Yes.
And here we see the opposite. What going on? Welcome to modern reality. What's in here?
Okay.
See, there's something on a wooden base. What is it? Let me draw. I have real DC source. First capacitor just to filter. Key element. I have a switch. I will draw it as a switch. Coil. Diode to discharge. Coil self-inductance EMF. Second condenser and a law. This switch, it's a transistor, is driven by a special circuit called PWM, pulse width modulator. PWM. It has a FP means feedback voltage on the input, and it sends command on off. This means that this point will be energized and de-energized.
The Ohm's law is applicable AC?
This thing anyway works on DC network. But it's
this one is applicable only DC network. It's not
yeah, AC needs a rectifier. We will see. Don't worry.
Okay.
I'll get it. Here you see voltage at this point. How the PV, what's the base idea behind PVM? One moment, I'll need you see, but let me move camera to make it visible to everyone. Bit down and. This is voltage after the switch. How PWM circuit works. The base version will need, it's the early version, you'll need voltage like this. Sawtooth voltage. This voltage is compared with green line, it's feedback voltage. So it's a feedback voltage. Switch state of the switch will be 1, 0, 1, 0, and coil will be energized and de-energized. If, for example, load increases, I put an additional resistance. See what happens. If load increases, this resistance decreases, voltage also goes down. Here, for example, this one is for a load prim, smaller, and a load. Like this. What will happen? We will see increase in the width of pulse. PWM, pulse width.
Pulse width modulation.
Yeah, pulse width modulation. So PWM circuit will increase the length. Watch it. try to catch it. Here. 1, 2, 3, 4. Approximately 4 widths only when I increase load and 1, 2, 3, 4, 5.
Okay.
Amount of energy this coil receives increased. Let's take an opposite experiment. Decrease load.
Okay.
See, we had load of 40 watts. I decrease it to the level of 19.
Okay.
What will happen? I can draw it here. Blue one. Width of pulse decreases. The blue one is twice greater than the green. Here it is. 1, 2, 3, 3.5. Pulse decreases, and amount of energy sent to coil also decreases. What will happen as a result? Take a look on this voltmeter. 12?
Yeah, approximately.
Let's show it to our. I can go closer to show voltmeter. Yeah. Right. Yeah. So at this moment, no load. 12. 25 watts of load. 12. 20. It been 12. Full load. Or 40. 12. I can change load in a quite wide range, but voltage will remain the same. It's a voltage stable, I think, or voltage conditioner if you want it. So this step down converter from 24 to 12 holds its set voltage, it's 12 volts. This I can change load in quite wide range, and voltage remains the same. But how will it react to the change of primary voltage? Not to change of load, but to change of supply voltage. I will move closer to this part. So maybe I can make also scope visible this way, and okay, I think it's sharp enough. How will it react to the change of primary voltage. I'm decreasing voltage. What happens with
The same works.
the same? I decrease voltage, current increase.
Yeah.
1. What is I have 20. Okay, I go down
Maybe 16.
16. Still holds. Let's see what happened with pulse.
Yeah.
It's lower in amplitude because I decreased voltage. But the converter needs to keep the same voltage. So it increases length of the pulse. Let's go in opposite direction. 26.
Maybe the amplitude will be increased. Yes.
Yeah, amplitude increases. And at the same time, length decreases. Power remains the same. Area of the pulse or energy supplied remains the same. So, we see something interesting. We see a load consuming constant power. Voltage changes, but power remains the same. Because control circuit tries to keep amount of energy load receiving constant, unchangeable. I can decrease voltage. Where am I now? This way more. This way.
Maybe you can decrease it below 10. What happened?
At some moment it will shut down. Yeah, it's
not shut down.
Yeah.
12.
It's an emergency regime.
Ah, okay.
Here, somewhere around 16 volts is margin of stability. Yeah, here is the lowest possible. Maybe I go. This is 16 volts to 20. Yeah, amplitude increased, length decreased. Area remained the same. More voltage, 26.4. Not that. See? Here it is. Amplitude increased, length decreased, area remained. But I have a problem. Oh. 26. One area. 17 volts. Here it is. Same area. I can change voltage in a broad range and power remains the same. I'm changing primary voltage, power,
The power
25 watts do not change. So what we see here is an object, nowadays object, let's say, it's a constant volt, ampere, constant power load. such thing is very typical to the city transports, like trams, trolleybus, commuter trains, and so on. Metro trains powered from 600 or 3000 volts DC networks. For such networks, we will see this effect. Understood. We will see this effect of P constant loss. This phenomenon, I should use word phenomenon. As you understand, this phenomenon, such kind of network is not linear. Classic theory of vector techniques will not work here. What can we do? What should we do? There is a trick. First, non-linear networks are not solvable directly by neither by technique of contour currents, neither by technique of nodal voltage. This will not work. First, we need to somehow reflect non-linearity of the law. And there is one of the way to do it, an idea, is to reflect this non-linear voltage as a controlled current source. So, load should be substituted with draining current source with the current is function of load voltage. In my case, it will be simple. Current will be power divided by voltage. Controlled current source, draining. It's first step. Second step, such networks, these transport networks, are always, they are regulated. At last, one powering station should be equipped with the voltage control system, keeping voltage at the bus unchangeable. It is necessary because load is very unstable, load of the network. We have night hours with very few traffic, and morning rush hours, also evening about 6 o'clock we will see a surge in load. To keep the network voltage in some reasonable, inside some reasonable margin, at last one of the stations should be equipped with the automatic voltage control system. At last one. Other station can operate by the power chart. So, network, something like generator, some power lines, loads, another generator will become a model like supplying power source, it will be current source. With the low, its current as a function of voltage should reflect governing control strategy of this generator. In the simplest way, it will be constant power. There are, in general, there are strategies PU, keep constant voltage, keep constant power, or P, simple P, or U, simple voltage. But if there is a network with a huge load, There may be multiple stations controlling voltage, and inner coordination is achieved by Drew. So in this case it will be U, but U as a function of current. Okay, at this point for us is enough of the constant power. So this station is controlled by power, and this station should keep constant voltage, and it will be reflected. Lines will be resistance, but this one controlling will act as so-called select bus or balancing node. I will mark it with nice triangle, but it's base constant. It should keep constant voltage, not zero, but constant 600 volts, for example, for 610, something like this. It's a set point of government of control system of this plant. For loads, I will also, loads will be substituted with the draining. This one is supplying current source. Other one, so one station, select bus, fixed voltage. Other stations are reflected by current sources. It's usual. If needed, you can also use EMF if there is a voltage strategy. But usual strategy is power and current source is better. If needed, if two or more stations are keeping voltage, this means what there will be not current source but EMF. But it's a quite rare thing. Usually one voltage, other by power. Supplying source, draining source. Lines with their resistance. Here we have DC network, so only active resistance. This is our electrotechnics theory model. It's a bit different. In base electrotechnics, base node always has a zero potential. Here, not zero, but fixed potential of the voltage governor. It's a difference. To make things be organized, we can introduce a power vector. It's made by nodes, conducted by nodes, and if generator is attached to the node, we will write it with the power with the plus sign. If load, we will write it with the minus sign. Now, what can I do? I can move to the nodal voltage equation system. I will need first incidence matrix. It's a branch nodes. I will also need resistance matrix. And I will use my first and transpose nodal admittance matrix. I will write nodal admittance method or nodal voltage method equation system. It will be dO plus, if needed, usually this part is not active, usually it's not used. What about this one? What is it? Here I have a matrix. It's II simple. Zero exclude E equals matrix of powers. Power by node. I will change from 1 to number of nodes. This one, y inverse I is again voltage of I node. What about this one? In our case, base node, not grounded, but base node is energized, and current can flow from base node. So I need to reflect this current in my first Kirchhoff. The base of all this is the first Kirchhoff. So here are conductivities between nodes and the base node. No problem to get it. Base node conductivity number I is a sum from 1 to number of nodes Gi for all I from 1 to number of nodes. It's a sum of nodal conducting matrix row elements. This is easy. Not easy. Fact that this system is not linear. It cannot be solved as a classic linear algebra system. How? How can I solve it? What should I do? There is no direct analytical solution. But it is very easy to find a numerical solution. Remembering what there is a technique of sequential approximation or iterative approach. What's the idea of Seidl's technique? For example, I have a system of linear equations. I can create a sequence. 0 will become x1, x1, x2, so on. X previous becomes x next, and at the end I should get a real solution. So this progression, this row of x vectors leads to a real solution. How can I organize this system? Seidl's techniques tell me, create a, let's say, conversion or the step or iterative matrix C in form. Sorry, I'm divided by I. For each I from 1 to number of equations, so from 1 to number of equations, form a bi as a bi divided by I, and do steps from previous to next, from previous to next, from previous to next, in the kind x I next should be sum from 1 to I minus 1. Ci x. Next, plus sum, where m should go from I plus 1 to number of iteration, Ci x previous plus di. Precision you can estimate as max by I y x next I minus x previous I as a maximum absolute difference. Very nice. What do we have here? We have next one closer to solution and previous one. In our case, if we apply this technique, what we will have? We will have previous voltage we can introduce x1, x2, x3 coordinate system. Here somewhere is a real, meaning a cross point of the straight lines, and we started from some x0, made a step to first, from the first to second, and so on. Understand it? The same thing will be with voltages. We will have a voltage space, and in each step we will have two voltages, previous and next, less precise and more precise. And then it should lead to this point of solution. So we can apply Zeidel's technique in such manner. We need to solve all these sequence approximation techniques. Say what next is some kind of function of the previous one. In our case, what can we do? We can create C matrix, so C2 minus divided by for E and R, changing from 1 to number of nodes, and start a sequential process where next, more precise, voltage at the node I can be found as sum. It starts from 1 to I minus 1. What I'm doing, C I U next, more precise, plus sum where M change from I plus 1 to the number of nodes, C I N U N previous, not precise, plus, and here starts the trick. For classical system, this part is constant. In our case, it will be function of previous voltage. Controlled current sources, all this array, will receive their values on the basis on previous voltage. Understand it? In each step, I have two set of voltage, more precise and less precise. At the end, they will come together. But in process, they are coming closer and closer. And each step, I can use previous, less precise voltage to obtain magnitudes of current sources, and this way calculate new, more precise voltage. So, goes here plus 1 divided by I. I will have power at the node I divided by voltage at node I from the previous state plus I base node voltage. This should be done for each I from 1 to number of nodes. Here is the Zeidel's iterative form for constant power loads. It will yield solution in steps, closer and closer. It is suitable not only for constant power. Here you can plan your load or generator control strategy. You just need to set it in the form current as a function of voltage. I took the simple but very reasonable approximation of constant power. For other, let's say, as a model, you can use different strategies. But anyway, just reflect it as a current being function of voltage, and it will work. Of course, there is a question of precision. I need to stop my iterative process somewhere. No problem. It's the same trick of the classic Seidel. So precision can be valued as a mass by I next minus previous, and it will work. Now, what I need? More ideas in such calculus or such network calculus. There are two more ideas not present in the classic electrotechnic basics. These ideas are power flow. What is power flow? I have a network. Let's say generator, line, somewhere, customer, something. If I put a wattmeter in such way in my line, it will give me, I'll use this branch number. Yep. What is it's from Latvian Zaks? It's a branch power. This wattmeter will show me a branch power. So if there is a, let's say, one business, next business, who, see, it is possible situation, what we have, both generation and consumption at other end. Who's selling whom? If this is positive, these guys are selling to them. I have negative, we are importing. So power flows are in fact many flows by line. Power flow is what wattmeter planted in line will show. For our DC network, power flow branch will be QI multiplied by branch current if I not 0. It's a power flow. Who's selling whom? Another value is a DPC. It's a power losses. Is resistance multiplied by Ez square. It's a loss of power in a particular branch. When KPI, have you this KPI, key performance indicators, are calculated, the number one is technological losses in the network. When your bonus and benefits are calculated, number one is a sum of DPZ. It's a losses. It's what's going on, going out to the useless heating of wires. When you plan operation, if you will work with operation planning, reducing of this, increasing network's efficiency, will be paramount for KPI. So, power flows, it's system business related. We are selling them, they are buying, or we are buying from them, and so on. And losses, where is KPI for network efficiency. What can we do? We can take a look on the small real program, isn't it? We need to take a look on a small program. 1 second. 1 second, 1 second, 1 second. Where is my wire? 1 second, I will attach my TV. I will attach my TV here. I need to attach my TV, and here it is. Here is a program example. Program to calculate transport network. I will go step by step. Clear all values. This one, tick-tock, I needed to calculate an execution time. Not necessary. Matrix describing connections, nodes and branches. Maybe I can show it. Where is no. 1 second. This one maybe. Yeah, here is the network. One moment, I will try to bring it. Come on. Yeah, this one. One moment. Here is the network. Generators, loads. Which one? Yeah. This one was assumed, number 3, was assumed as a voltage controller. So, this one will be base node, and for As a network, what I need to do, I need to set numbers to the nodes, set numbers and direction to the branch, and I will get this incidence matrix, its connection between nodes and branch. Let's go forward. My next step, resistance. I took a bit simplification. I assumed that all lines are from same wire. It's just for simplicity. In reality, you will have a nice network drawing and so-called nice at last Excel table where all cable and overhead line specifications will be on your table. Just for simplicity, I have assumed copper wire 4 in parallel 4 by 125 square millimeters. It's just for simplicity. It's an old tram wire put in 2 on each direction and with joints. It's very typical for our city when forward line, backward line, and joints between them, and power from underground cable. Okay, it's just for simplicity. I have put a length of the, see, this vector in square are lengths in kilometers, and multiplied by resistance of 1 kilometer. It's just for simplicity. In real life, you will put your branch resistance from the network drawing. You will have this system with all the necessary.
Sir, in Riga trams are running by DC network?
Oh, sorry?
In Riga trams, transportations are running by DC network?
Yeah, 600 volt networks.
600 volt DC network.
Yeah, closest substation under the bridge, closest power line of terminal.
Okay.
This where two large brown steel gates and one smaller. It's it's double. It has two nodes, no, two base substation powering trolleybus lines. Yeah, they all are DC. And also these city trains are also powered by this DC 3000 volts. We will have AC 24 kilovolts when this Rail Baltica project will be complete. But now they are only starting. Okay, going forward, these are powers in megawatts. This 186. I have put power in megawatts and multiplied by 1.6 to get watts. Base node voltage 600 volts. So I have introduced my network to computer. Now calculus. MS, it's from Latvian Mezgo skaits, number of nodes. ZS from Latvian Zaro skaits, number of branches. What's this one? Why I'm filling voltage vector with the voltage of the base node. See, this sequence approximation or iterative process needs to start somewhere. I can assume that network voltage are not far from the this guided base, guided node. So to save time, I put a base node voltage as a starting point. this will save a bit of time. This one, I need inverse resistance matrix. Since only main diagonal is filled, it's very easy, 1/4 cycle. I will also need transposed first incidence matrix to conduct this. Actually, I need this nodal admittance matrix. I will not make it by hand. I just know what it's M multiplied by inverse resistance multiplied by transposed incidence. Next one, as I have written, conductivities to the base node. I need a direct conductivity between node and the base node. Since it's a sum of nodal admittance matrix rows, I will not waste my time. I will just calculate the sum and put them in corresponding position of the base node conductivity vector. Next 5 rows is this transfer matrix for classic Seidel technique, as we saw in linear algebra. Now key part, main Seidel solution cycle. I will repeat until precision is achieved. I have asked precision, take a look, 1 millivolt. For 600 volts, I've asked 1 millivolt. Okay, so I will write it again. Key iterative form. Nodal voltage for node I. Next, so more precise, is a sum that changes from 1 to I minus 1 Ci U. Next, plus sum changes from I plus 1 to the number of nodes C I M U previous plus again 1 divided by GI divided by UI previous plus GI for each I from 1 to the number of nodes. Here's my theory. Yeah? This row, blue row, is the square parenthesis. This part is a first sum. This part is a second sum. And precision, this part is to estimate a precision. Knowing what precision can be found as I to I. Next minus I previous. This part is to obtain precision, and when I have the next more precise voltage, I'll put it in the next place necessary. Branch currents by Ohm's law. Very easy. Next part. This part is for power flow. So branch power can be found as a node voltage multiplied by branch current, but I need to take corresponding voltage and current and knowledge of the first incidence matrix helped me. Losses. Here, with one cycle, I calculate each branch losses, and also this will present total power loss. Zud, it's a Latvian zudumi, in English it's losses. Branch losses, total losses. This small service, I calculate sum of the load to find these last lines. These lines are to calculate a total efficiency in percents and execution time. So let's see what happens. Yeah, where am I? Here are my results. Let's see, visible. I hope visible. Here are my results. So I got voltages. This, my boss will not have it if I present this. 481. It's a bit different from 600. So this network will not go. For such design, I will have problem with my salary and bonus. I got currents, I got power flows, some positive, some negative. I have branch losses, total losses, and efficiency 82%. I will not get my benefit if efficiency will be below 5%. If losses will be above 5%, sorry. So 95 is a borderline. If efficiency below 95, I will get anything but not my year bonus. I should do something. For example, I can, we see a quite large flows. I will say, boss, let's ask second station to produce a bit more energy. 77. Not a good idea. You know, boss, this network, we need to put more money in the network. See? 92. Yeah. And voltage are closer. What can I do? I can also raise base and also put more power here. 93. Voltage are good, but still need more. Okay, dear boss. Let's invest more. 95. Yeah, I'll get my bonds. Voltages quite normal, maybe better, but I'm above the cutoff line. It's all a process of optimization. The most probable task you can be paid for is to estimate efficiency and search the best possible. And search the best possible. Maybe I can put this example in a learning system. This is not. 1 second. I will put it. Oh, yeah, I feel it. Actually, I can feel it if we see. Who's present?
First one,
Yes.
then second one,
Yes.
then last one.
Yes. And
Last one too.
okay. Forgot it's on.
Yeah, it's the last one. Yes.
Wait 1 second. Saglabot. Something went wrong.
Yeah.
I need this one and see. Yeah. What I need a learning system. I will put.
So MATLAB file also.
I will put this example.
Okay.
But here, where are my? No. These are not.
Example.
Wait. This is not correct. This thing told me into wrong course, previous year. Where are my examples? Here are my examples. So I can add. Save and come back. But what? It is good and it is not good on the other hand. There is a good idea and not so good. What's not so good? I can explain. I have time for my explanation. What's not good? The Zeidel approach is working. It's really working. But it's relatively slow. We can do better. We can perform better. Let's take a look again. Equals to d inverse plus. Here is the equation we need to solve. This part is linear. This part, this one is not linear. If we can solve this separate already, we can boost up performance. The idea is to get inversion of the nodal admittance matrix. Sorry. Do something like this. This will yield us 1. This also yields 1. So we will get something like this. Voltage equals to dU plus, it looks like an iterative form. A form when sequential approach to the real solution can happen. Yeah? Just write here next and here previous, and you get something. Next as a function of previous. But not so easy. First, yes, if we get this inverse matrix, it brings us a very nice iterative form. Next will be sum change from 1 to I minus 1 inverse I multiplied by and divided by next plus sum from I to the number of nodes inverse Pm divided by previous plus base node voltage for I from 1 to the number of nodes. You can see it's an extension of the Zadel approach to, again, two sums, one with already known, let's say, more precise, and another with previous. But instead of Jacobi's semantics, which Zadel techniques inherited from the Jacobi method, I use inversion of the nodal admittance matrix. Inversion of nodal admittance matrix, in fact, means a solution of linear part. I have already solved linear part, so I'm only dealing with this non-linearity. It will boost performance approximately twice. Really. But there is one moment. I need to solve linear part. And solve it in efficient manner. I need this Jacobi symmetrics is very simple to obtain. This one is more complicated. But things are not so bad as you may expect. There is a Gauss technique of evaluation solution. Idea from the system A x equals to b, go to the system with triangular matrix. It's a Gauss solution. It's in all school books. But there is a derivative. Gauss' successor, Jordan, created his own version of this Gauss technique. In case Jordan's idea is go forward and not to create a triangular matrix, but to go to system with 1, 1, 1 known matrix equals to something. It's a Jordan techniques transforms original system to the form 1 multiplied by unknown vector equals to 3. If we write something like A multiplied by inverse equals to 1, yeah? It's from linear algebra. Yeah? Matrix multiplied by its inversion should yield 1. It's a matrix 1, 1, 1, 1. We can consider this as a linear equation system with set of and so on, set of unknown vectors being elements of inverse matrix, and this one will be B1, B2, B3, and so on, as a set of linear equation system. If we apply Jordan's technique to this, A will become a 1 unity matrix. This one will convert to inverse matrix. So idea of Jordan's inversion. If you have a matrix A, size n by n elements, you can assume it's an A0. From this you need to calculate A1, from A1, A2, and so on till AN, and it will be bingo, your inverse matrix. In each step, let's say I'm going from A minus 1 to the A, here, A should be from 1 to the number of elements. I'm performing a step from previous to next. For this step, A is 1 again from previous. It's so-called guide element. IK should be K previous A K should be minus R K divided by R K from the previous one. These three formulas, if I draw schematical my matrix, I will have row number K and column number K, let's say for the step number K. First one give me this element. The second one, where I change from 1 to the number of elements, gives me, and I should not be equal to K. This will give me, maybe this area, except the cross one. This formula is for full areas. So this cross will slide At the first step it will be here, on the second to 2, and so on. It will slide till n. And I'm missing something. I'm missing this part outside of the magic cross. Here also should not be equal to k. Important. For the part I marked with the red pluses, I dot except I equals to k, except equals to k. Next will be r I dot minus 1 main dot 1 minus 1 divided by k minus 1 for starting from 1 and ending to the number of equations. This is Jordan's inversion technique. It will allow us, Jordan's inversion technique allows us to obtain inverse nodal admittance matrix. It works both for AC and DC networks. It's the way to boost performance. It's a bit tricky because this Jordan's process itself requires m cube operation. But in reality, we dealing problems of best one. Find the best mode, find the best ability. In such problem, usual network itself, line design, line connection remains the same. We only change loads, power, so in such case network topology remains the same. We need to perform this operation only once. Solution of regimes with different generation and so on will go much faster. What I need to show how it works, yeah? One moment. If I found it, I can find my... Aha, here it is. And what's going on here? One moment. Yeah. So here is solution of the transport network with the help of Jordan's matrix inversion. Yeah, it's yes, it's okay. Everything fine. So first I am declaring this nice Jordan function. It's a Jordan's inversion. I use a bit interesting technique. I calculate this key element, this cross point. Then I calculate the special row and column. In a minute, I just take elements. Next, in this area, to avoid checking am I inside this cross or outside this cross, I first, in a kind of bulldozer, calculate them all, and then, see, I have saved in two vectors elements of this special cross. I put them here in a cycle. So first, I calculate everything ignoring this special cross, and then I put cross in place, substituting wrong values. And of course, I need to put white cross point elements. So here is Jordan function. It performs matrix inversion. When I have invert matrix, same incidence matrix. This part is the same as we already saw. No, nothing special. And here and here. Here I'm calling my function to obtain inverse nodal admittance matrix. And here is the key part. It's in fact it's a Zeidel technique. I can repeat it. It's a Zeidel, but instead of Jacobi C matrix, I'm using inverse nodal admittance matrix. It will give me much stronger converge process. Power flows, losses, efficiency, all the same. Maybe I'll take, what have I altered? Execute. So, execution of this version. 108. Sorry, my mistake. Okay, it took 4 milliseconds to obtain all this efficiency, voltage, currents, power flow, branch losses, everything in 4 milliseconds. To compare, where is my 14 equals to 4.
Yeah, equal to 10.
In a pre-execution time, wait, 4 milliseconds with matrix inversion and 14 milliseconds with the Zeidel. Zeidel works slowly, and one moment Zeidel speed of convergence, this convergence process of Zeidel technique is much dependent on the network load. Highly loaded networks are at the border of capacity are known when the network is loaded up to its capacity, the method, this modified, will converge very slowly. Inverse matrix application of inverse matrix much better. But you paying with n cube operation to obtain this inverse matrix. Jordan's procedure requires some calculus time. But in general, this approach, Zeider based on inverse nodal admittance matrix, performs better. It's my, let's say it's my favorite. But it's more complex. It requires, to perform it, you need this nice Jordan function to obtain an inverse nodal admittance matrix. That's it. Zero viewers for today. Yes. What should I do? This is wrong. This. Bunch of examples. Okay. So we can solve. Now we see how we can solve a DC network with constant power or any controllable law. Just substitute the simple current as a power divided by voltage with some kind of feasible representation of load strategy as a current by it should be informed current as function of voltage, and it will work. You will get result. None of theory, electrotechnics theory books tell about. Okay, I don't see online viewers, so I can stop the stream.